In this video, I'll show you how the quasi-hyperbolic momentum and Adam optimizers works, along with their interesting result on benchmark datasets. We'll look at the paper, the equation, the code, and some proof to get a good intuition about how everything ties together. QHAdam in particular is interesting because there seems to be direct improvement over many popular Adam versions without much performance penalty. The algorithm reduces variance, manages stallness problem of momentum-based optimizer quite well, and is generally very efficient. For those that are new to the channel, I'm Yassine, a published researcher and machine learning practitioner who love to teach. In this tutorial, we will go through these 5 sections. In the first 3 sections, we will understand the intuition behind the formulas and assess the 2 algorithm performance. In the 4th section, we will look at a naive Python implementation to get a feel about the algorithm mechanism. And after that, we will do a deep dive into the others' code in Pytorch. Finally, we'll take a look at the appendix of the paper for the motivation of how the other came up with the form we've seen earlier. Like with all seemingly complicated topics, take a deep breath, we will work on this slowly, and by the end of the video, you should get a very solid grasp of what those quasi-hyperbolic optimizers are doing. With all that being said, let's first go through a quick overview of QHM and QHAdam. The 2 formulas from this paper have the following forms. Both are anchored on prior well-known algorithm, namely momentum and Adam. At first glance, it might look like there's a lot of moving part. However, the change brought by the others is pretty minimal, although it has a very strong theoretical foundation. The momentum formula can be seen at the top, with the momentum buffer G being the crux of the implementation. In a nutshell, it is taking into consideration the past gradient buffer with the hyperparameter beta to make the next step. Momentum introduces a kind of leaky average to stochastic gradient descent, and it has some nice property, especially in variance reduction. Now, QHM simply add a new parameter called V, or the immediate discount factor. This parameter does a weighted sum between the stochastic gradient descent form and the normal momentum form seen above. It seems a bit counterproductive here, if you think about it, that we're bypassing the stochastic gradient descent by taking the past gradient into consideration, and then in the very next step, we are reweighting what stochastic gradient descent will do still. We'll go into depth in the Appendix A, a discussion at the end, about why this works. But at bird eye view, the other wanted to make an optimizer that can achieve like these 3 things. They wanted to make an optimizer to reduce the variance, like with momentum, without having the momentum buffer making the optimizer too much bias. So there's a trade-off between variance and bias here. All the while keeping efficiency high to make the optimizer practical for real-world use case. The interesting thing with QHM is that the form it used can recover directly 6 other optimizers, including Nesterov accelerated gradient and accelerated stochastic gradient descent. A very similar idea to QHM was applied to the numerator and denominator of the Adam algorithm, which hold the 2 moment buffer. Again, you can recover a few versions of Adam like RMS prop and NADAM by playing around the 2 immediate discount factor. The addition of these 2 parameters that does a weighted average of 2 quantity is the only change brought in by both algorithms. Let's look at the performance of these algorithms now. The other tested various parameters during each of their experiments. We'll mainly look at their best performance in the following graphs just to get a sense of if this is helping at all. There are a few models being tested here, so with a few datasets, so don't hesitate to pause this section to really grasp what the setting was. The main result for the parameter sweep experiment can be summarized over here on these 2 datasets and network. As you can see, these networks aren't state of the art, it's more for benchmarking purposes. First, we have a simple multi-layer perceptron with the extension of the MNIST dataset with QHM. The eMNIST look like this. It's a mix of letter and symbol, which is a step more complex than pure MNIST. QHM was better than the best Nesterov accelerated gradient optimizer, but by a small margin. We have the same setup, except we swapped the QHM optimizer for QHAdam, and then we're comparing Adam RMS prop against QHAdam. And the gap between Adam and QHAdam is quite visible here too on the validation error. Finally, we have ResNet 50 here on the ImageNet for image classification. And this one is a bit more of a tie. Both NAG and QHM perform relatively similarly. After this parameter sweep, the other decided to try to hit state-of-the-art result on various benchmarks using bigger models. They actually managed to do it on a translation task. We'll see it in a few. Same here as before, pay close attention to the naming convention as it will tell you exactly what experiment was being run. Let's start. First, we have ResNet 152 on ImageNet for QHM. QHM and NAG have comparative result. However, QHM converge faster. Then we have a FConv model for language modeling with Wikitext and a QHM. And QHM here outperform NAG by half a point in perplexity. Then we have a transformer with a translation task from English to German. QHAdam, even though it's not 100% clear here, reached state of the art on that task. Finally, we have three set of experiments with reinforcement learning and with the twin delayed deep deterministic model. First model that we use here was the ANT model, and which QHAdam yielded better average return. Same setup, but now with the half cheetah. Hard to say here because of the scale, but it also have a better average return. Then we have again the same setup, but with the hopper structure. And this one, QHAdam has an apparent better average return. It's important to note that in the three other reinforcement learning tasks that are not shown, Adam actually performed a bit better than QHAdam. To summarize, the simple change brought into QHM and QHAdam seems to help the performance of these algorithms across a wide range of networks and tasks. Let's now break down the formula of QHM and QHAdam, starting from the primitives. It's not that complicated, you'll see. And here we are. So I cut out all of the stuff that is important, starting from the primitive all the way down to the algorithm QHM, and here QHAdam, we're over there. All right, so let's start with the primitive. So the building blocks that we have here, we have the parameter theta, which is like the actual parameters for our model. There's this thing, the loss function that we're using, and it's named L. We actually have L at, which is our approximation of the loss. And after that, we build on that, we have the gradient, and we have the gradient hat at some point over here, right? So we have to take it step by step because there's so much parameter in this, especially in the QHAdam. But as we're going to go through it, you see, we're just going to add one bit at a time. So starting here, this is a general kind of formulation of a gradient optimization algorithm. So you have the new parameter equal the old parameter minus something. Now, the easiest algorithm is the stochastic gradient descent because it's the new parameter is equal the previous parameter minus a learning rate times the gradient. So that's what it means. So the gradients are important and they will come in all of the other algorithm. If you don't have them, it doesn't work. If we go and we add a layer of complexity, we have the momentum version of stochastic gradient descent. And it's the same thing as this, except we have a weighted, kind of a weighted average between two quantities. So we have the normal gradient over here as if we were doing stochastic gradient descent and something called a GT. So if we go step by step here, we have G, which is called the momentum buffer, right? And the basic idea of momentum is that you're gonna keep in memory some information about the previous gradient, the optimization that you were doing, right? So that's kind of the idea of it. And then there's like an average that you're gonna take between that and the new gradient. And this is controlled by this variable B, beta here, which is called the exponential discount factor. Because in a nutshell, this whole thing, it's called an exponential weighted moving average. We're gonna see that a bit more in detail afterward. This is good because it reduces the variance when you're doing the optimization step versus stochastic gradient descent that will have higher variance, but it biases a bit more your algorithm performance. Anyway, so we have this variable, and this is a hyperparameter that you're going to tune. Usually we say like in the high 0.9, and that's it. It's like 0.9 times the previous momentum buffer that we had in memory at the previous time, plus 1 minus the exponential discount factor times the current gradient that we have. And that thing is what we're going to use our learning rate on to do our steps. What QHM is doing is it will add another component on top of that. We have pretty much the same thing as this form. It's this part over here is exactly the same. There is absolutely nothing that has been changed over here. The only thing that is changed is over there, right? Where we were supposed to have the GT plus 1 like this, right? Instead of having that, we have, again, the same trick. And again, we're doing kind of a leaky weighted average between two things. And instead of an exponential discount factor, here we have an immediate discount factor called V. And this whole thing is basically what it's called a V weighted average of the momentum update step and the plane stochastic gradient update step. So now let's play a bit with the parameters to kind of understand what is going on. So we have the same formula here. So this is QHM. So if we have here two things basically. We can do stochastic gradient descent, because if you see here, we have 1 minus v times just this. And this alone, if you like erase everything else, this is stochastic gradient descent. We already seen this form. And then this part over here with the v is actually stochastic gradient descent plus momentum, right? So the v is controlling this and the 1 minus v is controlling that. So theoretically speaking, if we put like v equals 0, it means that we're doing none of this. And then we're basically just doing stochastic gradient descent. Even though we're calculating this, we're just disregarding everything that is here. If we're actually doing a v equal to 1, it means this one is 0. So this is limited, and basically we're doing only stochastic gradient descent with momentum. This whole part get erased, basically. So usually we have a mix of both to make it QHM useful. So you should see that the QHM, like just the formula speaking, as a continuous form that is in between doing a pure stochastic gradient descent optimization step, or a pure stochastic gradient descent with momentum step. Somewhere in between, you can retrieve Nesterov accelerated gradient and a whole bunch of other algorithm if you want to. So if we continue a bit our descent toward like QHAdam, it's going to be the same idea. We saw the formula, the form that it takes, but now we're going to use the Adam algorithm. So if you're wondering what Adam is, this is the whole algorithm. It has a different form because I took it straight from the Adam paper. So it's actually like a pseudocode formula type of thing. There's a bunch of variables that are different than like this formula in this paper, but we can go through them. We have the learning rate here. We have beta 1 and beta 2, which are the exponential decay variable for the moment estimate, because in Adam there's like two buffer we're keeping. F is technically supposed to be L here, but we can keep F in this thing. Theta is the same thing. You have M and V that are our moment vector here, and T is still the time, and that's it. And then with this, we can actually build up the formula. So G over here is our gradient. So it's at this form with the L. It's what we had previously. So you have G over here. So M is our first, we said bias moment estimate. So here we are taking beta times M plus 1 minus beta with the gradient. So this is the same thing as what's happening in momentum. If you look here, it's kind of the same thing that is happening with momentum. You keep one of them, and then you do this with V, but V is a bit different. It's the same form, but you're gonna you take the second raw moment estimate. So you just square the gradient, and that's it. There's some correction because this is bias, we're saying, and then there's some correction that we're applying over here. And once this correction is applied, then we have this form for the update of the parameters. So it's the unbiased first moment divided by the square root of the second moment plus an epsilon, just that we don't divide by 0 at some point. A lot of variable, but if you go slowly through it and you write it down, it's fairly understandable. Now, take a snapshot here. We're going to go and see QHAdam. And it's a lot, I know, but like it's the same stuff. Like these two things is exactly the same as like this whole algorithm. Everything here is the same. The only difference is over there, right? So if you look here, the only difference that we have, instead of having the first moment divided by the square root of the second moment plus epsilon, we still have that, but we've put a V, which is a discount factor, the first one, and 1 minus V over here. And we're doing the same thing. We have like here our, well, could look like stochastic gradient descent form. And we're doing the same thing below also. It's not exactly like a one-to-one correspondence about what's happening in QHM, but it's fairly similar idea. And that's that. Like that's the two changes. And if we look at it at the same view as QHM, and then we're trying to change some variable, here we have two parameters where we can change the variable. So we have the first immediate discount factor and the second one. And if we put both at 0 and then 0, what we'll get is we're gonna get this knocked out and this knocked out, right? So we get only this left, and this will be a 1, so it doesn't exist. This is also going to be a 1. So we're going to take the square root of the gradient here, right? The gradient estimate. So that's just the gradient estimate. So you have the gradient estimate divided by the gradient estimate. You have nothing here. And then the epsilon is whatever, right? It doesn't matter. So there's absolutely no learning that will happen whatsoever in this form. It's just literal garbage at 0, 0. If you have 1, 1, what you get actually is going to be these gone, right? These two. So you're going to retrieve Adam over here, right? This is exactly Adam. And if you have V1 equals 0 and V2 equal 1, so basically you knock out V1, you're going to knock out this part at the bottom. What you're actually going to get is this form. This is RMS prop over here. So if we look at it as like a plane, at the lower end, we have no learning. At the upper end, we have Adam with V2 and V1 equal 1. And in between, you have the other form. So here, you have Nadam over there. If you have V1 equals 0 and V2 equal 1, you have RMS prop. So this whole thing, this whole plane is actually QHAdam, right? And then when you play with the parameters, there's like sweet spots where it's much performant than like all these other ones. By the way, if you have a hard time reading math in deep learning paper, I made a video on the technique I used a few weeks back. Now that we understand the main equation, let's check what an implementation would look like. We'll jump into now a very naive implementation of QHAdam, to say the least, which isn't efficient at all since it's just pure Python. But I'll put emphasis here on readability over performance. Okay, so here we are in the notebook. So like be prepared, the code is fairly crappy, but it's very readable. It's just Python, there's no NumPy. There's a bunch of algorithms that we've implemented over here. The one that is of interest right now is QHM and QHAdam. So let's jump into that. The model we're going to use here, the dummy one, is just like a line. We're just using a line here, very simple to go through it. And then we're going to use that as the function to optimize using gradient-based algorithm. So a bunch of them. Here we have QHM, and then the type of formula we're going to try to approximate is like this. This one is intercept 0, slope 1 with the data. There's this other one which is intercept of 0 and slope of 2, and then there's a third one. So if we look at the algorithm, we have QHM here that is implemented. We have a bunch of stuff. We have the model, we have the data, and we have the hyperparameter. So let's go through it slowly. First, we initialize our moment buffer with literally nothing, right? Zeros. And then we're gonna iterate per iteration that we set the maximum number. Here is 1000. And we're taking one sample because it's stochastic. There's no batch of any sort. It's just like we're taking one sample. We're using that to calculate like the next step we need to take in the space. So here we're taking the gradients, we're calculating them, and then we're taking our past moment buffer. And what we're doing with this, like a for loop, basically we're doing our beta, or decay factor, times our moment buffer, plus 1 minus the beta, the decay factor, times the gradient. So it's literally this part that we're replicating, right? Except we're not doing like vector. It's just like literally one by one that we're doing. This is why I say it's so inefficient. So the second line here, right, is it's pretty simple. So we have the weights, we have the moment buffer, and then we have our gradient, and we're gonna do it like one by one. But basically it's the weight minus the alpha learning rate times something, which is like a weighted average between two things. One of the thing that it is like the moment buffer, right? So we could literally go all in and do a stochastic gradient set with momentum, or just the gradient, which is just doing stochastic gradient set. It's literally that part and that part that we're replicating. And that's kind of that. So if we run that, should be good to go. And if we run this one, QHM, to our surprise, it's actually working. So we have with the intercept 0 and this to be 1, the slope. So if we are replicating this down with this one, so this one also we got it, it's 0, and then we have a 2. over here, right? Good. Last one is intercept of 1 and slope of 2, and we got it. So good work. All right, so let's jump into QHAdam now. So same form, we have model, we have the data over here, we have the learning rate, beta 1, beta 2, v1, v2, epsilon. We have all the variable over there. A lot of them, but it's the same thing as before in QHM and momentum, but it's a bit more complicated in terms of steps. So if we look at it, we have our first moment buffer here that we're initializing, second one over there, the one that is squared. We are keeping track of our gradient because we need them. And then we have the same loop of iteration, right? We take one sample at a time, we calculate the derivative with that, and then we calculate our first moment buffer and then our second moment buffer here, right? And if you look at the code, we're taking the gradient and then we're using our exponential discount factor, and same thing, the second one, and this one is the gradient squared, which is this thing over here, right? Exact same thing that we're doing here. We call this G in our case, and in our case this is M and then this is V, right? Every time you're looking at code or a formula in the paper, just be aware of what the variable means, because if it's letter, it doesn't mean anything. You have to swap it in your mind what it means. The nomenclature I'm using is this one. I literally replicated what was in the Adam paper. Then we bias corrected them, both of them. So this is the first moment buffer bias corrected, second moment buffer bias corrected. They have the same form with different B's, as you can see just over here, right? This is what we're doing over here. And finally, this is the meat of it, right? So you have like the model, the first moment, the second moment buffer, the first moment buffer, and the gradient that we need. And then we're doing the same stuff as before. We have the weight minus learning rate minus the whole thing with the numerator and denominator. At the top, we have one minus the first discount, immediate discount factor times the gradient plus the V1 times the first moment buffer corrected, divided by, and then you have your square root stuff, right? That finish here just before the epsilon. So you have 1 minus V2, and then you square your gradient plus V2 times the second moment buffer corrected. And this is squared. That will give you like the top and bottom, divide, and then you multiply by the learning rate, and then you can update your weights. Which, if you remember, this is exactly this exact form that we have over here. Perfect. So if we run that, it's good. And with the intercept 0 and slope of 1, we're gonna run it. And we have for QHAdam, we're good to go. It's not too bad. 0 here and 1 over there. And for intercept 0 and slope of 2, we have it's converging, and we're good to go here. We have 0 over there and 1 over here, 0.999, so 2 roughly. And for intercept of 1 and slope of 2, what do we have? We are good to go, 0.99, so basically 1 plus 2 over here. So it's kind of working. Let's now look at the real implementation in Pytorch from the others, from Meta themselves. You'll see there's major difference in the structure, readability. We'll go through it slowly, but it's not that complicated. Okay, so now we're gonna take a look over here at the QHM update from Optim repository from Facebook Research. So it tells you how to use it, and this is basically Pytorch. The actual code is hidden over here, QH Optim. I think it's Python, and then we're gonna see it here, QHM. So you have blah, 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 all of this over here, right? And same thing for QHAdam, you have it over there. Yeah, the code is fairly straightforward. It just has a lot of boilerplate and stuff. So we're gonna actually take some snapshot and then only take the meat of it that we're gonna decipher. Okay, so we have the QHM code, the part that is important here, 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 and here. And we also have the QHAdam that we're gonna do over there in a few seconds. Let's start with the definition at the top because it's important. So LR is our learning rate. Here we have our momentum. So it's basically beta in the paper. We have a nu over here, which is the immediate discount factor. So it's the V that we were seeing. So we have the weight decay over here, which is not useful for our stuff right now because it was not in the paper. So you can disregard this part. So keep in mind these three things: LR, momentum, and nu. They means that alpha, beta, and the V. here we're initializing our stuff. This is fine. And then in the step, this is where things are starting to pan out. So don't worry about this. We're just getting our parameter out of like the variable that we need. And then this is where we actually are doing stuff that is useful. So P here is the parameters. So it's our theta, right? So P is our theta. And what we're doing at first is we're taking the gradient information over here. So dP is our actually our gradient. So weight decay, you can kind of forget about it. It's kind of not important for us. And then this is the only code that actually matter, right? That's just where everything is happening. So we have our momentum buffer, right? Which we call I believe in our stuff is called G, right? And then what we're doing is we do that multiply by the momentum, right? The momentum is the variable. In our case, it's beta, right? And then we add that plus here with this form. This you have to be a bit careful. What we're doing is we're doing this plus, like what we said, plus this, and then we're going to multiply the two together. It's a bit counterintuitive, but like it's a good way to optimize your Pytorch code. So we have this times the gradient, and here the gradient I will pull it. How is it called? This L of the parameter, like that hat, right? All of this stuff is our momentum buffer G, right? So we have that over here, and then we're doing this part over there. P is our parameter, remember. So we have our parameter theta plus, because we're doing add over here, and then you have these two that are multiplied, but also these two that are multiplied. So you have our learning rate, which is minus the A over here, times our V over there, times our G over here. And all of this goes straight into our theta, right? And here we can simplify a bit. So we have theta minus A times V times G, right? And then we're adding this straight up, like we're gonna do this again. So we're gonna do plus here, and it's the same thing. It's gonna be minus A times 1 minus V times the gradient. Right. Yeah, you have, if you're not familiar with these formulation and these tensor function, you just look at the Pytorch documentation. It's really well explained. So we have this, right? We're getting closer to like our actual formulation. That makes sense. So here we're doing the same trick. So we're going to do the minus alpha 1 minus V still here times our estimate of our gradient there. Boom. Right. And then you see these two are the same. We can just take them out. So we're just going to do like this. A times, and then we have V dot G plus that whole thing over here. Poof. And we're good. And if you remember correctly, this is the same form as before, right? So this, same form as that. So if we double check, right, that we're doing everything correctly, this is G times beta plus 1 minus beta times this, our gradient. And that part that took us 2 lines actually to get through, right, give us the theta minus the alpha times this big thing, which is that part, the momentum buffer times the immediate discount factor. It's a bit like permuted, but it doesn't matter. And we have 1 minus v here times the estimate of the gradient. So we're good to go. Okay, so let's take a look at the QHAdam code right now. Same thing as before. We're going to take a look at the variable first. So we have here the learning rate. Same thing. This is the alpha. This is our betas. This is our v's, right? Immediate discount factor. And we have our epsilon. So everything is all good. It's those two that have a different name. You can see here, like the default value, we have B1 0.9, B2 0.999, and by default the V's will be 1, 1. And remember, 1, 1 means Adam, but that's kind of it. So if we take it slowly, we have the same structure here. At this point, this, we know what it is. It's going to be our gradient, estimate of the gradient over here. And then this is good, this is good. We're not doing that. And over there, we're going to multiply this by itself. So we're going to square that. Let's follow. So we're good over here. So we have the basic component, we have this component, we have that component, this one, and now we have to build the rest. Nothing important here except a different initialization for the first round. Then we have our first thing that is interesting over here, the beta 1 weight. As you can see in this code, it's a bit different implementation than this. It still gives the same effect as before. But we'll see it in a few. And after that, with our beta weight, we're gonna do the beta adjusted, and then we're gonna do our first moment and our second moment buffer. So let's take a look at what's happening over here. So what we're saying is that we're gonna do 1 plus beta, let's say 1 times something, beta weight. At the beginning, the beta weight will be 0, so 0. So first iteration, we're going to do 1. That's the second iteration, because you see we're always messing around parameters that are saved repeatedly. We're going to do 1 plus beta 1 times what was there previously, which is this thing, which is 1, right? So this is 1 plus b. And then for the next iteration, we're going to do 1 plus beta 1 times what was there before, 1 plus beta 1 equal, and if we fix it up, we're going to have 1 plus b1 plus b1 squared, right? And this will just keep increasing again and again. So we're going to have 1 plus this, tac. However, we are at in the time. This is how the summation will look like. So with that being said, this is the form of the beta weight. We're then going to adjust them, and how to adjust them is we're going to do 1 minus 1 divided by this thing, right? This is what we have. So what will happen here? So at first we only have this term, then we have this and this term, and then it will kind of keep increasing like this. If this keep increasing, the bottom part, it means that 1 divided by something that gets bigger and bigger, it will just be closer to 0. So here we're gonna keep decreasing from 1. So if this is decreasing, we're gonna have 1 minus a big number, and then it will gradually go down here, right? So at first, for this whole thing, we're gonna have the smallest number it can, and then it will just gradually increase inside. So for the first number, we're gonna have 1 minus roughly 1, which is gonna be 0. So b will be 0. So this will be knocked out. This will be 0. So we're just gonna take care of the gradient. Effectively, at first, we don't care about the gradient buffer, and then more and more as we go forth, we're going to care more and more about the gradient buffer, which is effectively what Adam is all about. So with this beta adjusted number over here, 1 and 2, we're effectively going to do this first moment buffer. It's called, in this case, G. So we're going to do G multiplied by this new beta that we have here, right, that is adjusted, plus 1 minus this beta that is adjusted, right, times this. And this is that adjusted. It's good. And we're doing the same thing for the other one. So we're going to do S times B adjusted. So this is the second one. This is the first, right? Plus 1 minus B2 adjusted times, you see here, we're using the squared version. So it's going to be this thing squared. And this is exactly this part. So far we're good. There was nothing too outside the box. And then there's a bit of complexity here. You see, they did something very clever in order to avoid calculating stuff which is not needed, right? So if V1 and V2 is 1, it's effectively Adam. And if it's Adam, we don't need to do 1 minus whatever, right? Remember, the Adam part doesn't have that, doesn't have that and doesn't have that. So with this gate, they're guarding against that. Let's remove this one, let's remove this one, and let's assume the epsilon is not 0, right? So we're going to do this 6, 1, 2, 3, 4, 5, 6 steps. So let's do them slowly. So we're going to have the average grad here, which is going to be this part that we calculated, the G. I have the G times V, and then here we're going to have plus 1 minus V times the gradient, right? That part, average grad, right? And here we have average grad RMS. Is this is average grad, and this is average grad RMS. I think root means square. And that's that, because at the end, we're going to do minus alpha times, and then this top divided by this bottom over here. Okay, so we're good. And now we have the second one, which is going to be with the squared here. You see, it's this one that we're using. So it's going to be S times V, and then we're going to do this plus 1 minus V times this would be the second one, first times this one squared. Good. And then we square root the whole thing, boop, and this step over here, and finally we're adding the epsilon in the other step. All of this we're gonna take, right? This whole thing we're gonna take over there. We're gonna take this whole thing over here also. Then we're gonna do a division, right? Addition, C division, and then we do A times this whole thing. And then we add it to P, which is our data. And there we go. That's how it looked like. This form is exactly this form. The only thing that is a bit tricky in this code is that part, right? And I'm guessing they're doing something clever with this formulation over here. And now that we have all of this intuitive knowledge about QHM and QHAdam, let's jump into the core motivation that the author used to make this optimizer. Okay, so now we're in Appendix A, a very important section of the paper for many reasons. It explains, yes, the motivation between QHM, where it came from, but also I think it teaches you something a bit more deep about the result in machine learning in general that are getting discovered. Because these results are, how to say it, they're not coming out of like fundamental at first. They usually come from experience, and then the theory get tacked upon it, and then we discover something fundamental. But there's always an important nugget in this, and in this paper particularly, they were very transparent about like how they came up with the stuff, and the part that is important is this, right? That's kind of the crux, right? So they had an intuition and whatever, and then they said, in preliminary stochastic optimization experiments, we did observe a marked benefit of this thing, hyperbolic discounting, over exponential weighted moving average momentum. Limiting number of path gradient used for tractability. This indicates that time inconsistency might be useful property to have in a stochastic optimizer. So this is sandwiched between their whole narrative here, but effectively they were messing around that part, right? Because someone had an idea in the lab, and then they tested it and it was like, yeah, it could work. And then they went back, justified it, and then improved it, and then they got into the result that was interesting. Because that part over here didn't sprout from first principle to start with. It sprouted from an idea, and then they linked it all together. Okay, so let's take a look at it. Basically, they start from primitive here. So basically, they define a discount function, this sign, and they're defining the discount sum as this thing, which is equal to the summation of the discount function applied with I times the data, basically. Then there's two things that they're defining: the discount sum average, which is has this property, and discount sum average modulo initialization bias, which has this other property. It comes up afterward, but for now you can like discount it. Then they define the exponential discounting with a form that is taking with the exponentially weighted moving average, EWMA, right? Basically, they define this discount function as being this one, an exponential discount function, and they're applying this to that form over here, right? And in that form, the 1 minus b, you can move it up, and you can just keep the b exponent I, and then you have your thing over there. This thing, what they're saying, that the momentum buffer GT is a EWMA of this form. You see, we have I equals 0 bi, but we have times xt minus I. So let's start with the first I of 0. What happened? We have b0 time xt minus 0. Okay, and if we continue until the end, we have bt times xt minus t. So 0 effectively here, x0. So this is telling us that at I equals 0, so the first I that we're looking here, which correspond to the last time for the sequence. So the last element that came in effectively is the least discounted in this sum. And then here, it means that the element that first came in will be the most discounted if there's a long string of time. So momentum is like this. That's what we're saying. Momentum, the momentum buffer here behave like this. And I found this great answer about why it's a EWMA. And let's say you pick a gradient component, let's say GA over here, right? And then you look at the I, so the iteration. The first iteration, you're gonna get this form, right? Because it's literally this. That can be simplified to just this, okay? Second one, you're gonna do, because remember, we're gonna put the momentum buffer back here in the next iteration. You're gonna get this plus 1 minus b at GA2. Right, so you get that. This is the gradient that you just calculated here. Okay, cool. And as you go in the third one, what you get is the pass 1 times beta plus 1 minus beta of the gradient you just calculated, and if you unroll it, you start to see a pattern here. If you unroll it some more, right, you start to see a pattern. What you're seeing as a pattern is that the first element, so the first gradient you calculated, it gets like discounted and then discounted and discounted again and again. So basically what it means is that it's getting discounted exponentially, and in a nutshell, the old term will die out to insignificance after enough iteration, depending on the value of v, but like it will be the least significant amount. So this is good, and what they're saying then is that this is a time consistent discount function because of this ratio over here. So that setup, right, make it good at variance reduction. So if you calculate the covariance matrix and you get like an estimate of the whole variance, what you're gonna get out of this is that the b is what is modulating the variance, and if the b is greater and greater, the variance will just shrink to nothing at some point. And it makes intuitive sense here. Let's say you take this and then you pick the biggest b you can think of, which is 1. What you're gonna get out of this is you're gonna get a 1 here and you're gonna get a 0 here, which effectively means you learn nothing, right? You will bias this function like crazy, but there will be no variance here. It's good to reduce the variance, but we should not be biasing it too much, right? As we increase the b, the variance decrease, but we have this thing that is called staleness, which the momentum buffer gets so clogged up that we're just kind of stuck with this, and then it's becoming what they're saying slow to update. So this is the motivation that I've discussed in the deck. The question they wanted to ask is how can we achieve variance reduction while guaranteeing that like the most recent gradient will actually contribute to making a step and not get slower and slower. They are saying we need to introduce time and consistency, which, like, spoiler, this is what they tested over here experimentally, and actually it helped. So what they did is they picked one time inconsistent discount function, which is the hyperbolic discounting form, which has this form. This is the function, the discount function form. And this is used in behavioral economics. So there's a bias where humans prefer immediate reward than delayed reward, even if it's greater. So that's what they took over. And then when you do the same test for time consistent or inconsistent, you get this, right? Because of the many variable that you have here. So it's inconsistent, it's time inconsistent because this test here depend on both I and tau, and not just tau. Cool, this is great. It's not practical for many reasons, but you have to decay the learning rate at a logarithmic rate in order for this to be valid. But practically you can't do that. There's something else that is existing that approximate an hyperbolic discounting function, which is the quasi-hyperbolic discounting. And it was used by Lepson that popularized it in 1997. It has this form. So the first step is doing something wonky, and then after that it follows kind of a formula. And if you look at it here, this is the first step, do something kind of hard-coded of some sort, and then it follows the function, whatever the function is. So if we go back to our stuff, they define the quasi-hyperbolic discount function as this one. 1 minus v times a beta, v being the immediate discount factor, and the beta being the exponential discount factor, the same one as the momentum, if I equals 0, and if I is bigger than 0, you have this form instead, right? So v times 1 minus beta times beta exponent I. That's what you get. So you get this soup of letter QHWMA, but you can construct your discount sum in this following form. So first you have that, but then you can do some algebra trick to jam this back in there, and then you have I equals 0, and then you have this form. So when v equal 1 in this particular setup, you get this killed off, and then you get this at 1, so you get 1 minus b. You get back the exponential weighted moving average that we were talking before, which aka is akin to momentum in our formulation of QHM. So this is why you can have this oscillation between stochastic gradient descent and momentum. So you have the test that we're doing over there for if it's time consistent or inconsistent, and it's actually inconsistent because of the first thing over here. This doesn't just depend on tau over here, it also depends on I. With this definition, it's like we said, it's a V weighted average of the exponential weighted moving average. And here it explains why it is efficient and it's easy to track. So here we have the this form that this is taking, right? Proof is in G, it doesn't matter here, but essentially if you can scale the beta and the V, and then you can modulate the variance of your stuff. So now you don't just have the B that you have to jam up and it will lead to more biases. You can actually be a bit more fine-tuned in between. So now we go to the motivation of QHM. So what they said is they're just going to replace the EWMA, discount sum, with QHWMA, quasi-hyperbolic, and that's it. And with this, they'll have all of their cool property that they were interested in. They can now play with these two parameters. So B can be increased toward variance reduction, so by lowering this quantity for the variance. And then you can play with V to decrease what we've done in the variance to make it a bit less biased. So make that the newest newest gradient that are entering the whole soup have more weight. And if you go to the extreme here, what will happen is that you will just take these into consideration and not the past gradient that you accumulated. And voila. So that's the motivation that the author went through in order to come up with QHM. But like you saw, it was sandwiched between like some experimental stuff, and then they were able to go around and then attach everything that they needed in order to make something coherent. One thing here that is interesting is that you might think that if it's true that the V and the B are like playing together to increase the bias, and then why not just have B equal V times B? But here in this specific part, they show that this is not equivalent. Like if you jam them there, you actually end up with this form, which is not what the form of QHM is. So QHM, even though it looks simple, has some nice property. And the property that is the most important is that in a nutshell, it adds another knob to fix the bias that is very, very fine while you fix the variance with your beta. And that's it for today. I hope you enjoyed the video. Don't forget to like if it was the case, or leave a comment if you have any question. I'm here to help. Have a great week, everyone, and see you in the next video. So that's it. This is the plain stochastic gradient descent. If we go and we add a layer of complexity, we have